Welcome to the OpenMP booth talk on using loop transformations with the Clang compiler. I'm Michael Kruse from the Argonne National Laboratory. Let's first revisit the loop transformations that were introduced in OpenMP 5.1. Even before OpenMP 5.1, we had several compilers already implemented some kind of Unroll directive, but with different syntaxes shown here. With OpenMP, we had the idea to standardize these under a common syntax, which work across multiple compilers with this syntax. So pragma-OP unroll full would stand for the same code, but with an unroll loop, and would behave the same way as if the user had written the unrolled code in the first place. Alternatively, if the loop's iteration count is not known at compile time or just too large, the loop can also be unrolled partially. This would coarsen the granularity of the loop as shown on the right. It would also care for if the iteration count is not a multiple of the unroll factor. In a third mode, the compiler decides what unroll factor to use. The compiler would use the information about the target architecture to choose something sensible, but not necessarily the optimal one, since there are a lot of things that determines the efficiency of the code that is not known at compile time. The other loop transformation we introduced is tiling. Tiling can apply on multiple loops, in this case 2, and it's tiled in a 2x2 pattern. The final code and illustrations look like this. So we ensure that the inner loops are at a maximum size of 2x2. If the loop iteration count is not a multiple of the tile factor, partial tiles have to be introduced. In this case, the compiler will have to handle the execution of the partial tiles and is also allowed to optimize it separately from the complete tiles to allow more opportunities for optimization. Compared to most compiler extensions, it is noteworthy that the OpenMP loop transformations allow composition of transformations and directives. One can think of any loop-associated directive to apply to what comes on the next line. This can either be a literal for loop or the generated loop of a loop transformation construct. In the examples shown here, think of the tile construct, including its loop, to be first replaced by the tiled loop nest, then the task loop is applied on that loop nest. A task loop without collapse clause is associated with only one loop, such that it would only generate tasks for the iterations of the outermost loop and contain the innermost loop. This is similar to what the grain size clause would do. Combining two tile directives allows optimizing for multiple levels of the cache hierarchy. For instance, one can choose a tile size that fits into the L1 cache and another tile size for the L2 cache. Such nesting will get significantly more complicated with more loop transformations, especially with partial tiles involved as well, and I'm glad that the compiler can do this for me. Next, let's talk a bit about my implementation of these loop transformations I did in the Clang compiler. That is, I already gave a talk about it at the LLVM in Parallel Processing workshop, which was part of the International Conference on Parallel Processing this August. The recording of it is available, shown at the link below. My talk starts at about minute 37. Here, just a little teaser about what I did. This is a representation of the internal architecture of Clang with its several layers. The transformation had to be implemented mostly in the SEMA and the Cogent layer. The implementation has been recently released as part of Clang 13. It actually contains two implementations. The default implementation based on AST transformation is ready to be used and is the one I'm going to showcase later. Another implementation for the OpenMP builder is currently in development. Its advantage is that it can be used from other frontends as well, including MLIR and Flang. So next, let's go into some performance engineering using loop transformations. I'm going to use Google Benchmark for this. Google Benchmark is a library for micro benchmarking. One of the things it does for you is to not count the initial called executions as part of the for using the calculating the average execution time, and also executes the code until it thinks that it's statistically stable, that is removing noise from the measurements. To do this, we put the code we want to measure inside this loop over the state, and we will stop if Google Benchmark thinks it has enough numbers there. We can use it also with templates. So we have a template parameter P here, so we can instantiate the benchmarking with multiple values of P, which will later be useful, so we can use different unroll factors here. We can do the same thing for offloading as well. The only difference is that we want to do the transfer between CPU and GPU separately. So we put the pragma target data map before the state loop. So it's excluded from the timing measurements here. But otherwise it's the same, but we explicitly wait for the target task to finish. Otherwise it would just continue to launch the next target region while the previous one has not yet finished. If we do this, we get something like this. So this is the final executable linked to the Google Benchmark library, and it's executing the code with different parameters for the chunking. So the first one is with no chunking at all, and afterwards we're using a chunk size of 1, 2, 3, and so on. What you can see is that the one without chunking is actually the fastest. The chunk size is determined dynamically, whereas executing each chunk imposes some overhead. And when using just a chunk size of just one, we have lots of chunks with lots of overhead as shown here. For experimenting with full unrolling, we are using the SU3 Matrix-Vector Multiplication, which is used in lattice QCD applications. We have two loops here, both with a trip count of 3, which we both can fully unroll. This constant trip count is quite bad for the branch predictor of a CPU, because it will usually assume after three iterations that will continue iterating, but at the fourth it will stop the loop. So this will be a branch predictor mismatch, which would be better if we would have just straight line code. To compile this, we're using this Flame. The first line I probably don't need to explain, but FOpenMP is for enabling OpenMP compilation, and we also need to select the OpenMP version because loop transformations are new in OpenMP 5.1, and the default OpenMP version is OpenMP 5. So we need to explicitly enable this. Then we also disable the native loop unroller and loop vectorizer in LLVM to not interfere with what we specified it. Of course, if we want to test our own unrolling, we don't want to the compiler to unroll itself, but we also disable the loop vectorizer because LLVM's loop vectorized path has an optimization called interleave, which is pretty similar to unrolling, basically vectorization, but not using vector instruction. And we want also to avoid interference with our measurements with that one. We can also use the rpath flag to get information from the LLVM optimizer, what it actually does. For the code on the previous slide, it outputs this. So it says for the 2 loops, completely unrolled loops with 3 iterations, which is a confirmation for us that it actually has done something. If we look at the actual performance numbers, it looks like this. This is an Intel Xeon processor, and we have 4 possibilities on how to unroll it. As expected, the slowest one is if we do not do unrolling, and the fastest is if we unroll both loops. And if we just unroll one of them, either the outer loop or the inner loop, we get something in between. For a different Intel processor, we get also different results. This is clocked a bit faster, so in total it's a bit faster than the previous Intel processor, but for it, it's less significant which of the loops we unroll, as long as we unroll at least one of them. And only when unrolling both, we get a bit more speed up. Same thing with an AMD processor, an AMD EPYC. But in this case, it did not matter at all which loop we unroll, as long as we unroll at least one of the loops. I also did the same experiment for an NVIDIA Tesla GPU, and it did not show any sensitivity to unrolling. So it could be that maybe it did not do unrolling, or maybe the driver, when receiving the PTX instructions and compiling for the actual hardware, would do unrolling itself. Because of this, NVIDIA supports a unroll partner to tell it either to unroll in by factor or to not unroll at all inside the NVT-PTX code. And we can see whether it's inserted using the save temps plan. This will write out a file. This is OpenMP nvtptx64.s as for assembly. And there we can look whether it has been unrolled or not. And what we see here is obviously that we find the now unroll partner there, and hopefully that would mean that the driver did not additionally unroll our loops, such that we can say that the NVIDIA processor was not really sensitive to unrolling and latency hiding due to instruction fetching worked quite well. For testing partial unrolling, we use a different program, which is atax, typical linear algebra kernel from the Polybench benchmark. There's an outer loop which we do not touch, but 2 inner loop which we want to unroll by the common factor, which we specified via a template parameter, as we have shown with Google Benchmark before. We are compiling it basically with the same parameters, and again, we're using rpass to confirm that the compiler is actually doing the unrolling. This is with heuristic unrolling, that is, we don't specify the partial clause at all, so to leave it up to the compiler how much to unroll. And the output shows that it has decided to unroll by a factor of 8. We're going to see whether this is a good choice or could be better. So this execution on the AMD machine with no unrolling or an unroll factor of 1, we have the worst performance. And the more we unroll, the better the performance gets, until we reach a maximum of an unroll factor of 128. I assume this is because the inner loop reaches the bounds of the L1 cache. So if the innermost loop contains instructions that will not fit into the L1 cache, you get a lot of L1 cache misses. I tested other processors as well, but none of them showed really sensitivity to the unroll factor. So the AMD processor was the best to show this. We are again moving to another benchmark for testing the tile directive. This is the Heat 3D benchmark from the Polybench benchmarks, which is a stencil application. Stencils usually respond well to tiling, so we expect some speed up here. Noteworthy is the choice of the tile sizes. So I left 8 as the innermost tile size to not interfere with vectorization of the innermost loop. And the other two dimensions are getting the same tile size, P, which is the template parameter. So this is a rectangular tile with a quadratic part, T times T, and 8 in tile size 8 in the innermost dimension. We also apply collapse 3 when parallelizing it. So the three outermost, the floor loops, can be executed in parallel and not just the outermost loop, which would be generated from the I loop, which would significantly interfere with the possibility to parallelize this. So the results, what we get is here. First, we have one with actually no tiling at all. We just apply static and the collapse 3. So there's just one stencil update per iteration, which execute in about 1.6 seconds. Then apply a tiling by 1 by 1 by 8. It's a bit slower, but from then on, when we increase the tile size, we get a faster until we reach a minimum of 1077 milliseconds by 5 by 5 by 8 tile. So we can say that tiling improves performance. It also gets worse the larger the tile size is, because the larger the tile size, the fewer tiles we can parallelize between the cones. But this could also mean, therefore, that this is a result of the tile size. So therefore, I did additional measurements. So first, we have the blue bars, which is the same as we did before, which is everyone uses schedule static without specifying chunk size. Then we have the red bars, where we apply a chunk size of 1. This means that a single thread, when it finishes one tile, would not execute the neighboring tile, but jump a bit, which would show, in theory, gives you worse locality. And it shows here as well, since the red bars is always slower than the blue bars. It goes into the extreme at the bottom, which is probably the case because the inefficient handling and work imbalance due to the partial tiles, which have less work and are relatively large. The ones without tiling is where we put the chunk size to make them the same size as a tile would be, but the order in which the stencil updates would be executed is a lot different. Specifically, would not make use of spatial locality due to the tiling. And as you see here, it's indeed a lot slower. It does not actually vary that much, giving a different chunk sizes. So we can definitely say that tiling gives some performance boost here due to improved memory access locality. I did the same thing as well on NVIDIA Tesla GPU, where we could give show a speed up to a factor of 3. Again, with a 5 by 5 by 8 tile size, showing is tiling is really useful. We are reaching the end of this talk. I just want to conclude with a quick summary. First, I mentioned the loop transformations, tiling and unrolling, which are new in OpenMP 5.1. I implemented those in Clang 13 and used them to do some performance engineering using the Google benchmark. Specifically, I tested full unrolling, partial unrolling, and and tiling, and could show some real speed up using those. But the outcome actually depends on the processor architecture you're targeting on, so you need to know to test what parameters to use to get the best performance out of your code. By just adding some pragma to their code instead of what you usually do for tiling, you would need to restructure your loop nest code. For OpenMP 6.0, we hope to add more transformations and other improvements, such as an apply clause, which would allow not only to apply more loop-associated constructs to just the outermost loop, but also to generated inner loop, for instance, from a tile clause. I thank you for your attention. We have more talks in this OpenMP Booth Talk series, which you can see on the openmp.org website. Thank you.